I should mention you do not have uncertainty in all cases. If you think about it, the previous measurement, the latest measurement that you performed, once you've done the measurement and you've got the result, then if you do the same measurement again, you will have precision. You will, with certainty, know the outcome. You will know what the measurement result is. Because remember, when you do the measurement, when the wave function before the measurement is a general superposed state, it's a weighted sum of eigenstates of the observable you're measuring, then after the measurement, the wave function will be one of those eigenstates. Right? So if you do then the same measurement immediately after, say like 2 measurements of A, then you know with certainty what the outcome will be after the second measurement. It'll be what you got after the first measurement, right? So I mean, it's not the case that everything's uncertain. There are saying here that if you do the same measurement immediately after the first one, you know with certainty what the result will be. All right. Now we can express a bit more mathematically, in mathematical terms, the criterion, the mathematical test, whether 2 variables A and B are compatible, right? And that test is when the 2 observables A and B have the same set of eigenfunctions. Right? Now, the previous session, I was saying that if you measure A and the result is lambda k, so the corresponding eigenfunction is psi k, and if that psi k is equal to one of the eigenstates of observable B, in other words phi k, then you'll have compatibility. Now it's saying much the same thing, it's just reworded a bit differently. Okay. Now what I just said is equivalent to the 2 observables A and B, well actually A hat and B hat in terms of their operators. So the 2 operators corresponding to observables A and B, in other words A hat and B hat, those 2 operators A hat and B hat have the same set of eigenfunctions. Think about that a little. They're equivalent. Okay. So eigenfunctions, eigenvectors, eigenkets, lots of labels for the same thing, right? Now, writing it this way allows you to find a much more compact mathematical criterion for compatibility or incompatibility, and it's the following. Now, here's your eigenequation for measuring A. Here's your operator for A, and keep forgetting. Right? And here's your eigenequation for B, for observable B with its operator B hat. Okay? So take your first eigenequation and multiply on the left by B hat, the operator. So you have BA equals B lambda. Okay? Now lambda's just a constant, so it can so you'll have B lambda, but it's a constant, so you can just rewrite that as lambda B. So lambda B, right? But B hat psi is the same as B hat phi, if you like. But we're assuming psi, the set of the eigenstates of A is equal to, they're just the same set as the eigenstates of B, right? So in other words, you, instead of, well, yeah, here it is saying they're both. We're using size for both. Okay, so b psi here it just becomes mu psi, right? Now let's take this one and multiply on the left both sides by a hat. So you'll get ab psi equals a mu, but mu's a constant, so that's the same as, rewrite it as mu a psi, but a psi is lambda psi. Okay, so you'll get mu lambda psi. Now the order of psi or lambda psi, they're just numbers, so AB is the same as BA. FG, two numbers F and G. FG is the same as GF. Okay, they're just numbers. They numbers commute. Well, these numbers, they're just complex numbers. No, they're real numbers, right? Because they're eigenvalues. Right. So real numbers commute. Yeah, you can swap them. The order, swap them around. Doesn't make any difference. 2 by 3 is the same as 3 by 2. Okay. Okay. So now subtract from this. Which way are we going? No. From this, subtract this. So in other words, from this, subtract this. Sorry. From this, subtract this. And since this and this are the same, that means that a hat b hat minus b hat a hat psi is naught. Now this is true for any psi. Okay, so you could have different wave functions here, and it'll always be 0. So that means that this what's in the brackets here, this a hat b hat minus b hat a hat must be 0. Okay, follow that logic. Now, and that has to be so because this equation is true for all. Remember the mathematical sign for all? Looks like a capital V with a sort of arc. So the for all, for every sign in mathematics. Okay. Now this a hat b hat minus b hat a hat, it's given a special name. It's called the commutator. To commute just means change the order, swapping the order of two things to commute. Okay, so this is the commutator or the commutator of two variables. Actually, they're not the variables, measurables. Sorry, it's measurables. Observables. Lots of terms to memorize, okay? Observables. Okay? So strictly speaking, the commutator is not of the observables, it's of the observables corresponding operators, right? So it's not as though it's like AB minus BA, it's the hat, it's the operator corresponding, so it's AB minus BA. And so this is rewritten in a shorter format with square brackets and a comma. There's a comma here. Okay. And this commutator is defined as just A hat B hat minus B hat A hat. Okay, so this square bracket thing is called the commutator, and the commutator is of two operators. Right? And the two operators in this case are the corresponding operators of the observables A and B. Right? Okay. Now, if this commutator is 0, then these two operators are said to commute. Remember, to commute just means to swap the order, and there's no difference. So if you measure A and then B, you'll get the same result as if you measure B then A. Like if you look at this, the A operates, now it's an operator, right? The A operates on this psi n first, and then you get a result, and then B operates on the result. So you operate with A, or A hat, first, and then B. And in this case, you're operating with B first, getting a result, and then operating on the result with A hat. Okay? So the commutator, implicitly, the commutator is suggesting first operate with A, then with B. And if there's a difference, or if there's no difference doing that, and then between that and doing B first, so B hat, then A hat, if the difference is 0, then those two operators commute. That's the terminology used. Okay. So in other words, we now have a very compact criterion, mathematical criterion, for compatibility of two observables, and that is that their commutator is 0. In other words, the two operators, A hat, B hat, of those two observables commute, right? So the square bracket, well, you can't see it here. If that's 0, then the two corresponding operators commute. Therefore, the commutator is 0, and therefore the two observables A and B are compatible. Okay, quite a bit of terminology there, a lot of new stuff thrown at you. All right. Now let's generalize a bit. So far, we've been talking about two observables, A and B, but we could have more, right? For example, if observables B and C are compatible, then you have a transitive relation. That's from pure mathematics. Do you know what that means? If A is a descendant of B, and B is a descendant of C, then C is a descendant of A. Right? Such a relation between A and C, or A, B, and C, is transitive. It goes, so the middle term B, it works across B, so from A to B and B to C, hence A to C. An example of a non-transitive relation, like is a friend of. So if A is a friend of B and B is a friend of C, it does not follow that A is a friend of C. Okay? That would be a non-transitive relation. But in this case, in quantum mechanics with compatible observables, it is transitive. So if A and B are compatible and B and C are compatible, therefore observables A and C are compatible. And of course you can continue on, right? I mean, you may have a fourth variable, D, that's compatible with A or B or C, doesn't really matter, right? They'll all be compatible then. So you can have a whole bunch of compatible observables, right? You can have that in quantum mechanics. All right? Now there's a bit of general stuff, sort of a little bit of housekeeping, tidying stuff up a bit. If you have a wave function, psi, and you know that it's that there are two observables, so let's say, well, A and B, but to keep things concrete, imagine the two observables, so say the energy and the momentum. Now, we know that those two are compatible, the E and the P, right? So instead of labeling the wave function here with